If you've ever sat at a dinner party with a half-empty crystal water glass, you've tried this. Blow across the rim, and it hums. Pour out a little water, leaving more empty air in the glass, and that hum drops to a lower, deeper pitch. The note you hear is entirely dictated by the volume of empty space. That auditory trick is easy to observe, but the sound wave actually leaving that glass is completely invisible, radiating outward at a blistering 340 meters per second. Pinning down the exact speed of something you can't see, moving that fast, feels like it should require a high-speed camera or a laser grid. But you don't need millions of dollars in lab equipment. You just need to understand the physical geometry that traps an invisible wave. We can measure the exact speed of sound using three completely mundane items: a standard smartphone, a tall plastic cylinder, and a pitcher of tap water. Together, these items create a physical snare. We're going to build an acoustic trap. By adjusting the empty space inside that plastic cylinder, we can force a sound wave to fold into a specific shape, allowing us to pull out a ruler and literally measure its size. We start by filling the cylinder to the brim with water. Then we place the smartphone right over the opening, playing a pure, constant 500 Hz tone. Right now, it's just a quiet, annoying hum. But as we open a valve at the bottom and let the water begin a slow, steady drain, the column of empty air under the phone starts to grow. The sound remains steady as the water drops, until it hits one very specific millimeter mark. Suddenly, that quiet hum erupts into a massive, overwhelming tone. This intense acoustic spike is called resonance. The smartphone didn't turn up its own volume, so the question is how a random pocket of empty air suddenly turned into an amplifier. This diagram shows what happened inside the tube. The sound wave traveling down from the phone bounced off the water and collided with itself, forming a perfect standing wave. Look at the bottom boundary. The hard surface of the water physically prevents the air molecules from moving. This forces the wave's displacement to zero, creating what physicists call a node. Now look at the top. The open air at the rim allows the wave to vibrate freely at its maximum amplitude. We call this an antinode. This specific shape, pinched at the bottom and wide open at the top, locks the geometry. It means the empty space inside our tube represents exactly 1/4 of the sound wave's total length. If the tube holds 1/4 of the wave, we simply multiply the length of that air column by 4 to get the full wave size. Multiply that by our 500 Hz frequency, and we calculate our velocity. It is a clean, elegant textbook equation. But if you actually do this experiment and plug your measurements into that formula, the speed you get is wrong. The math failed because it assumes a perfectly rigid, flawless universe. To get the real speed, we have to account for the physical messiness of the actual room. The first crack in our perfect math comes down to how sound behaves right at the exit of the tube. In reality, a sound wave doesn't stop flush with the glass rim, it bulges out slightly. This invisible overhang is the end correction. To fix our measurement, we add this bulge, roughly 30% of the tube's physical diameter, to our original length. Sound refuses to be neatly boxed in by our glass cylinder. We have to map the wave as it spills into the air outside. There is one final variable sabotaging our measurement, and it is the air itself. Sound is a chain reaction of gas molecules bumping into one another. If the room is warm, those molecules already have a higher baseline energy, which means they transfer that acoustic bump faster. This graphic maps the exact relationship. Base speed starts around 331 meters per second at freezing, but for every single degree Celsius the room warms up, the speed of sound gains an extra 0.6 meters per second. When we take our raw measurement, add the end correction for the bulging wave, and factor in the temperature of the room, the math finally locks in. Our plastic water tube yields the exact true speed of sound. Precision in a laboratory rarely comes from a flawless theoretical equation. Instead, it comes from measuring the chaotic environment we actually live in and doing the math to compensate.